Welcome to UGC's lecture series, ePathshala lecture series on computer science. The subject is Introduction to Visualization and the module is about visualization of tabular data. Some of the learning objectives of this module are, it will introduce the concepts of table data, what table data is, the various different forms of table data. We will also look at the various terminologies related to table data structure and table data visualization types. We will also learn about the different forms of tabular data, and then at the end we will look at various examples of tabular data visualization techniques. Introduction to tabular data. What is tabular data? Tabular data is prevalent in the form of spreadsheets and relational databases. The tables often describe multivariate data set, and the data is also modeled as a graph or a network for some kind of analysis. A table design usually conveys some static network semantics, and analysts may try to look at the multiple networks from different perspectives at the various levels of abstractions and with the different edge semantics as such. In most visualization that can handle more than 3 dimensions, we can fit our definition of table visualization as such. A 2-dimensional table of data is defined by m rows and n number of columns. A visualization of this data is termed as table visualization. In our definition, we often define the columns to be the dimensions of the variance, which are also called as fields or attributes, and the rows to be the data records. The data records are sometimes also called as n-dimensional points or cases. In geographical, scientific and imaging visualization, the spatial dimensions are normally assigned to the appropriate x, y and z spatial dimension. In a typical information visualization scenario, there is no inherent spatial dimension, but quite often the dimension is mapped to the height and width on the screen and has a dominating effect. For example, in a scatter plot of 4-dimension data, one could map 2 features to the x and y axis and the other 2 features to the color and shape of the plotted points. The dimensions assigned to the x and y axis would dominate many aspects of analysis, such as they are helpful in clustering and also helpful in outlier detection. Some table visualization, such as the parallel coordinates, the survey plots or radial visualization, treat all of the data dimensions in equally. These are also called as regular table visualizations or RTVs. The data in a table visualization is usually discrete. The data can be represented by different types such as integer, real, categorical, nominal, etc. These visualizations are also called as array visualizations because all the data that belongs to the table or that are present in the table are of the same data type. Table visualization data is usually not hierarchical in nature. It does not explicitly contain internal structures or links. The data has a finite set where m and n are bounded. The data can be viewed as m points having n dimensions or features. The order of the table can sometimes be considered as another dimension, which is an ordered sequence of integer values starting from 1 to m. If the table represents points in some other sequence such as time series, then that information should be represented as another column in table visualization. Now let us have a look at what recursive table visualizations are. The general logic diagrams were first discovered by Michalski and displayed only the Boolean data values. Later on, the Boolean inputs were extended to discrete categorical values or binned ordinal values, and these are used for general data exploration by Matt Wald. This technique is more generally called dimensional stacking and is implemented in the packages XMDV and MLC++, as well as the latest version of Mindset. AutoGILF also produces a display similar to dimensional stacking, but it is not recursive in nature. A 2-dimensional grid usually is divided into a set of embedded rectangles, which represents the categorical dimensions or attributes of the data. There are 2 outer dimensions along the x and y axis, and each additional pair of dimension is embedded into the outer level rectangles. In recursive table visualization, this recursive embedding continues until all dimensions of features are being used. Displaying more than 9 dimensions with this technique is usually very difficult. Each dimension should in turn be categorical or binned, which means it should be a discretized value with not much more than 4 or 5 categories or bins. These are artificial limitations imposed by the display resolution. Panning or zooming technique could avoid the need for limitations, but displaying whole picture at once is very difficult in this case. A final dependent dimension or classification is usually used to color or fill the smallest embedded rectangle in this case. The outer dimension or the lower speeds have a different effect than the inner dimension or higher speed dimensions. Hence, the mapping problem of which dimension to choose for the outer and inner representations become very significant. Because of the nested dimensions on the horizontal and vertical axis, the labeling also becomes problematic in this kind of recursive table visualizations. Differently sized grid lines should be used to emphasize the difference between a new nested dimension and the separate bins of a dimension. The method of binning or discretization has a strong effect on the visualization. Entropy based binning also helps separate the classes while keeping the number of bins very small. This can also reduce the number of data points with mixed classification in the final embedded rectangle. Dimensional stacking can also be used for finding clusters, outliers and patterns or rules in the data. Depending on the dimensional layout and the binning, the dimensional stacking can be an important analysis tool. In the next slide, we can see a dimensional stacking of the iris flower data set where some squares have mixed classification. The outer x-axis is a binned petal with a dimension. On the inner x-axis is a binned petal length dimension. The outer y-axis is a binned sepal width and the inner y-axis is a binned sepal length. The concentration of the 3 flower types are represented by the squares colored with 3 different colors, that is pink, yellow and green. So this is a recursive table visualization wherein we can have a look at various sepals and petals length and width for 3 different flowers as such. The next one is the multi-way tables. Like the scatter plot matrix for quantitative data, the mosaic plot generalizes readily to the display of multidimensional contingency tables. Imagine that each cell of the two-way table represents a hair and eye color and is further classified by one or more additional variables, that is a sex and the level of education. For example, then each rectangle can in turn be subdivided horizontally to show the proportion of males and females in that cell and each of these horizontal portions. It can also be subdivided vertically in turn to show the proportion of people at each educational level in the hair eye sex group. The dynamic pressure model extends readily to multi-way tables. For a two-way table of hair color and eye color, partition the sample space according to the marginal proportions of eye color and then partition the observation for each eye color according to the hair color as before. So this is a representation of the multi-way table as such. We can see the eye color in the first table and the hair color in the second table. The vertical representation shows the eye color and the horizontal representations shows the hair color as such. So the eye color as well as the hair color are shown in the form of a multi-way table. And in the same table, it is also possible for us to show the sex and the level of education of each person that are being identified. Within each column, the forces balance as before, so that the height of the chamber is given as NUV by N, and then the area of each cell in turn is proportional to the maximum likelihood estimate MLE of the cell of the probabilities NU plus N the whole into NUV divided by NU plus, that is equal to NUV by N, which is equal to P, which again is a sample cell proportion. For a three-way table, The physical model is a cube with its third dimension partitioned according to the conditional frequencies of third variable given the first two. If the third dimension is represented instead by partitioning a two-dimensional graph, the result is a mosaic display. It is a visual approach that uses circles to represent the rows in a column in a circular fashion and ribbons to represent the cell values. It also provides a way to capture the essence of table and present it quantitatively and attractively. So this is a different approach towards tabular data visualization that uses circles to represent the rows and columns in a circular fashion, and the ribbons are used to represent the cell values. So in this approach, the relationship between the data elements are encoded by ribbons that join the segments that correspond to these elements. So this is the kind of visualization which is also called as a circus that uses the circus to represent the rows and columns in a circular fashion. The ribbons represent the cell values as such. So here the extent of the relationship is represented by the thickness of the link, and a link can have variably sized ends to indicate some specific kind of ratio as such. So each and every ribbon or the link can be variably sized, which also indicates the ratio. The ribbons can have different thickness to represent ratio between the elements. By coloring the ribbon, that is by adding transparency to the ribbon, the representation can focus on the flow of information in a particular direction, either from left to right or to A, that is right. Normalizing the segments to equal size is motivated by whether it is absolute or relationships are going to be important. Some of the terminologies associated with this kind of tabular data visualizations are the table versus array. At times, we may use the term array when discussing the tabular data at the final visualization stage, where it is usually converted to array data. Multidimensional and multivariate dataset. In many data mining dataset, it is unknown whether a particular attribute or feature is independent of any other attribute. The more appropriate description is multidimensional, multivariate information visualization. Since dependent attributes should be termed variates and independent attributes should be termed as dimensions, at times we may use the word dimension when it could be either dimensional or multidimensional or multivariate. The next terminology is dimensional brushing. This is a technique for highlighting a particular n-dimensional subspace in a table visualization. Each dimension has an active range, and points within this active range can be colored or highlighted with a particular value. The visualization area of this brush is colored differently. Class points are the classification dimension. In data mining or machine learning, a special categorical dimension is often designated for particular classification. For example, in a data set called cars, which we use for the example, there are three classifications: American, Japanese and European. Additional dimensions are horsepower, weight, the MPG, acceleration, cylinders and ER. Although any dimension can be used for classification, data mining algorithms work better if the range of values of the classification dimension is going to be small. Points with the different classification like brushed points can be colored with different values. The other terminologies are jittering or agitating. This is a technique whereby data points in the visualization are randomly moved a small distance to improve the display or to reveal the obscured or covered overlapped data points. Splatting. This is a technique for allowing three-dimensional scatter plot points to have some transparency and get more points on the screen. Local normalization. Each dimensional range is sealed to be between 0 and 1, thus giving each dimension some equal weight. In global normalization, all data values are scaled to be between the maximum and minimum of all data values. The dimension that has the highest data value may have greater weight or impact in certain visualization. In many visualizations, this will have the same effect as not scaling the data at all. So some of the definitions of terms, the local versus global normalization. So here is an example tabular data where you have the raw data with MPG, weight and cylinder, and later on after local normalization where the values are tried to be represented between certain range, and after global normalization where all the values are represented within certain range. And typically for some visualizations or data mining algorithm, it is better to scale the data to a range between 0 and 1 or minus 1 and 1. The table shows the difference between local and global normalization for 3 records which is similar to that of the car data set. So here we can understand that in global normalization the values lies between minus 1 and 1, and in after local normalization we can see the values lie between 0 to 1 in each case, and after global normalization they try to match the value between minus 1 and plus 1. Next one is a weighted normalization. In most cases, local normalization is used for visualization. When many columns of the dataset are of the same type, it is convenient for those columns to have the same normalization. For full flexibility, it should be possible to transform each column with a different weighted normalization. Flattening. Expanding a categorical dimension in a dataset by creating a new unique category value with the data values becomes 0 or 1 based on the original category value of that record. So let us look at one example, that is a temple MV visualization. In the temple MV visualization system, the dimensional stacking idea has been used and extended, and this is combined with the idea of histograms and tree maps to produce an unique visualization. Here, the tree maps are a hierarchical visualization where the size of nested rectangles represent data such as the size and locations of files on the disk operating system. In Temple MV, Ted Michelson uses a similar idea with histograms nested within each other along the horizontal and vertical axis. Combined with binning, the nested labeling and some of the ideas of dimensional stacking, this kind of Temple MV visualization helps to see the dimensional interaction such as 2 or 3-way interaction that is difficult to be seen in most visualization. Like dimensional scaling, this visualization is difficult for initial users to understand. With the interaction, data probing and good labeling available in MV, it has been our experience that one can learn to understand this kind of visualization. So this is an example of the Temple MV visualization where you can see the entire data being represented in the left hand side, and the right hand side you have the scale values. So an example, the previous slide shows a 4-dimensional view of the car dataset. This is a 4-dimensional view of the car dataset, and a 5-dimensional view of the DNA dataset. This is a 5-dimensional view of the DNA dataset. The X and Y axis on the left in both the displays shows a nested binned dimension. So the X and Y axis shows a nested as well as binned dimension of the dataset, while the legends on the right hand side display how each dimension is being binned. The right hand side legend will describe how each binning has been done in this case, in both the cases. The next kind of visual that we are going to see is the Envision. When interactive 3-dimensional rendering became popular, it was quickly applied to visual data analytics. Dimensional stacking paradigm extends to an interactive 3-dimensional environment, and one might like to get a system similar to Fiener and Becher's Envision system. This system allows the exploration of n-dimensional functional spaces, but it could be adapted to n-dimensional datasets. To explore an n-dimensional function with this system, one recursively nests the dimension 3 at a time from outer to inner cubes, similar to that of dimensional stacking. The outer dimensions gets fixed to a constant value, while the inner dimensions are used to display 3-dimension function of a surface. A dipstick device on the screen probes the values on the surface. So this is the Envision, a 5-variable function that is being represented, and Envision is shown here. There is an interactive stick which is also called as a dipstick or a measuring device that helps us in learning the information that is available on the screen. The outer fixed dimension and the inner variable dimension can be resized and manipulated for navigation. It is not clear whether this nested dimensional navigation is better than other interactive techniques such as the guided grand tour or zooming and panning on a scatter plot matrix for visual data mining. It is likely that the data would have to be binned on the inner 3 dimension would be similar to standard 3-dimensional scatter plot. Sometimes they are also called as spin plots in statistics. Mindset now has a decision table visualization that are some of the features of Envision and dimensional stacking. Sample displays from Envision are shown in the slides. So this is a multidimensional function displayed with the help of Envision. So here we can see how the multidimensional data is being represented, and it is also interactive in nature so that the user can measure the values of the data set that is being represented as in the form of Envision. Next one is let us have a look at the various forms of tabular data as such. Tabular data come in many forms, each unique in its schematic and semantic structure depending on the technology used and the data owner's goal. The term tabular data is thus fairly broad and can be interpreted as either multivariate data or attribute relationship graphs. Single tables are pervasive in the form of spreadsheets and comma-separated value files. The next table also shows visits to the White House. For each visit, it records the last and first name of the person arranging the list, arranging the visit, the type of the visit, the date and location of visit, the size of the visiting group and the visitee's name as such. So this is a kind of table that has been developed using the White House visitors information. So this is a sample visitor information to the White House. Such tabular data are essentially multivariate data where rows represent entities or facts and columns represent entity attributes or other entities. In a multivariate data, explicit network semantics is typically absent. Multiple linked tables are pervasive in the form of relational databases, although the same table can also be described in spreadsheets. In a relational database, the ER model, that is the entity relationship model, typically underlies database design. Each row in a table represents a fact that corresponds to a real-world entity or relationship. For example, the table 2 represents facts about employees in a company, and the table 2b represents facts about departments in the same company. The two tables are linked by one-to-many department-employee relationship type. That is, one department can have multiple employees, but one employee can only work for one particular department. One-to-many relationships are typically captured by foreign keys in a relational database. In this, the department in employee table is a foreign key referencing the department table. So if we have the employee table with the first name, with the employee ID, first name, last name, and the birth date and the department in which he is working. Then we have the department table with the ID, the name of the person, the city in which he lives, the state, the latitude and the longitude. So the two tables describing the employees and the departments they work for. Forms of tabular data. Another type of relationship in the ER model is a many-to-many relationship, and this is being captured by a separate relationship table. For example, 3A represents selected facts about research grants awarded by NSF, that is the National Science Foundation. In the Information and Intelligence System division, table 3B represents the facts about each researcher. The two tables are linked by another table which represents a many-to-many work-on relationship. That is, one researcher can receive multiple grants and one grant can involve multiple researchers also. So this is that kind of table where you have the grant table, where you have what is a grant ID, the title for which the grant has been given, the program for which the grant has been given, who is a program manager, and what is the amount for which the grant has been given. The next table is a person table, wherein this represents the persons or the research persons who have received the grants, the person ID with the name of the person and the organization, the university in which they are working, with the grant that has been received and the role of the person, whether he is a investigator or co-principal investigator and so on. So these tabular data in multiple linked tables are essentially attribute relationship graphs with explicit network semantics. So they describe the connections between the employee and the department entities. Similarly, we also have a graph specifying the connection between two types of entities, the researcher and the grant, each with its own attributes. An online analytical processing database, unlike the spreadsheet and relational databases, is not built for low-level atomic operations such as insertion and update, but for analytical purposes. It also uses data cubes for better performance in operation such as slice, dice, roll up and drill down. The analytical power of this OLAP, however, is not suitable for network-based analysis because it usually focuses only on the inherent relationship between the entity attributes and assumes different entities are mutually independent with each other. As a result, the OLAP framework is not directly relevant for our purpose and focuses on spreadsheets and databases, which provide a basis for an alternative network-centric framework. The next type of form that we are going to have is a fractal form, which is another form of representing the tabular data, a multidimensional visualization, which represents a correlation between the dimensions recursively. One chooses a starting dimension that is represented in the form of a colored circle. The other dimensions are represented as smaller circles going counterclockwise around the main circle. The size of the surrounding circle represents the correlation coefficient between the first dimension as well as the surrounding dimension. This process is then repeated with smaller circles around each of the other circles representing the paired correlations. Dimensions that are highly correlated will have larger circles. Other statistical features such as standard deviation, skew and kurtosis can also be mapped to the roughness, tilt and flatness of the circle. This visualization is not of the data but a visualization of some of the statistical features of the data. The visualization suggests how other features of the data can be used in visual data analytics. So this is a fractal form display which shows the sepal length center, the petal length center, the petal width top, the sepal width bottom and things like that. So this is a fractal form visualization of the tabular data. The next one is an example of the candy data, which can be represented as an Excel spreadsheet where you have the various candies with the various features of the candies being represented and which can be visualized in the form of some kind of bar chart and things like that. So these are various examples of the tabular data as such. So this is which displays the calories in the common candies, and this is a representation in the form of a bar chart. This is another representation in the form of bar chart, which is also calories and which are calories that are present in common candies, with sorting and expanding the scale of the graph and allows all the labels to be seen as well as displaying a characteristic of the data. So in today's module, we have looked at what tabular data is, what are the various terminologies that are associated with this kind of tabular data, how the table data can be visualized, what are the various forms of visualization that helps in the proper representation of the tabular data, what are the different types of table data, and we have also looked at the various formats of tabular data as such. And at the end, we have looked at certain examples of tabular data visualization. Thank you.